I can't take this anymore. I just don't understand this. When will I ever need to know about the relativity of space and time anyways?
Hello. I'm the doctor.
What's your name again?
I'm the doctor. Pleased to meet you. Sorry about that noise. Something must have been wrong with the dynamorphic generators.
Alright. Thanks again?
Right.
I kinda need to get back to work here.
Right.
Right.
Space and time.
Yeah, I had to write a report explaining the equation and everything, even though I know nothing about it whatsoever.
Oh, I know a good deal of space and time.
Really? Mm-hmm. How? Did you major in it or something?
Well, not exactly. I was there when Einstein discovered it.
What? You were there?
Yes, I was there. Try to keep up. Do you want to learn about this or not?
Might as well, I suppose.
Well,
all right, doctor. Lay it on me.
Well, suppose I should start from the beginning. Before Einstein came along, space was thought of as an expansion where absolutely anything was possible. Nobody knew if space was really there.
I don't need a history lesson. I just need to learn about how this stuff works.
Oh, fine. Einstein's theory of relativity describes how time is affected by motion through space and how mass and energy are related. Using relativity, everything, your hair, the wall, the White House, is whirling through a combination of both space and time. Now, this combination, this mass...
I don't think I get it.
Well, that's because I wasn't finished, and I never will be finished if you keep interrupting me.
Well, I was
Wibbly wobbly! See, I just interrupted you, and you didn't like it very much, did you? No. Anyways, the motion through space affects the motion through time. Whenever we move, we, to some extent, change our speed through time. This is known as time dilation, or stretching time.
Right. Stretching time.
Right.
Okay. And how's that you know all this?
Interesting you bring that up. There's a lot you can learn from a screwdriver and a wooden box.
Right. Anyways, I also need to know about this component of the formula. It's T equals...
No. T naught equals T times the square root of the quantity 1 minus V squared over the speed of light squared. Now, it's interesting that you bring it up, because right about now, I was about to... Shall we?
Great Scott, I think my flux capacitor is broken again.
You use a flux capacitor?
I do, you know of it.
Of course I do. I had one installed in the TARDIS a couple days ago. Do you have any solutions for the uranium heating problem?
Well, you see, it all has to do with...
Okay! I'm done. Not that this isn't interesting to listen to and all, but who are you people?
I told you, I'm the doctor.
Dr. Emmett Brown.
Wait. The Emmett Brown, the Dr. Emmett Brown, Dr. Emmett Brown, first human to ever understand time travel? No, it's you. Oh, Oh, well, it's a pleasure to meet you, sir. It's an absolute pleasure, Dr. Edward Brown.
Yes, it is quite a pleasure to meet you, but I didn't think anyone was familiar with my work yet.
Oh, they will be. Believe me.
I'm sure this is going to turn into some interesting topic which I won't understand at all. But, Doctor, we really need to get back to the space-time formula.
Right. My bad.
Space-time?
Yes. Michael needs help with his classes.
Did you know I'm quite great at that stuff?
Well, I would be honored.
Well, weren't you in the middle of something?
It can probably wait. The formula for space-time is very interesting. Einstein used this equation to show that the relationship between time, t naught, or proper time, in the observer's own frame of reference, and the relative time, which is relationship by t, measured in another frame of reference, is the equation you have here, where v is the velocity that is relative between the observer and c is the speed of light.
Alright. V is the whatever. But I'm not sure I completely understand.
Oh, I forgot to explain time dilation.
Well, no wonder he still doesn't understand. In short, it is the stretching of time.
It occurs ever so slightly at ordinary speeds, but it's very significant when you get towards higher speeds near the speed of light.
Of course, you know what we measure time with, a clock. But a clock can be any device that measures periods of intervals, like the swing of a pendulum, the oscillation of a balance wheel, or the vibrations of a quartz crystal. Now consider a light clock.
Oh, that's quite impractical, isn't it?
Yes, but it is the best to describe time dilation. Now, imagine an empty tube with a mirror at each end. Now imagine a flashlight. The light would bounce back and forth between the parallel mirrors. The mirrors are the flash bounces indefinitely. See, if the tube is 300,000 kilometers in length, each bounce will take 1 second in the frame of reference of the NG, up and down along the long diagonal path like clock. So, if the tube was 3 kilometers long, each bounce would take 0.0001 seconds.
Now, suppose we view the light clock as it whizzes and whirls past us in a high-speed spaceship, or, never mind. Suppose we see it whiz and whirl past us in a flying blue box. We would see the light flash, bouncing up and down along a longer diagonal path, supposed to a straight and boring one.
Now, going back to the equation, the speed of light clock has no effect on the speed of light. See, the slowing of time is not particular in the light clock. It is the time itself that is moving, frame of reference. As viewed from our frame of reference, that slows. The heartbeat of the flying blue box occupants will have a slower rhythm. All events on the moving box will be observed by us as slower. We say that time is stretched as it's dilated.
Right. Now, you might be asking yourself, how do the occupants on or in the box view their own time? It's very fantastic, actually. Right, time for them is the same as when they do not appear to us to be moving at all. Now, for how the occupants view their own time.
They see our time as running slow, just as we see their time running slow. There is no contradiction here. It is particularly impossible for the observers in the different frames of reference to refer to one and the same realism of space-time. The measurements in one frame of reference need not agree with the measurements made in another frame of reference. There is only one measurement that we'll agree on.
The speed of light?
Exactly!
This is actually pretty great.
Is that a smile?
I think it is.
Oh, shut it. I think that does it.
There is one more topic I believe we should cover. Don't you, Doctor?
Of course. Something thought to be impossible. Something wonderful and brilliant.
What? What is it?
Time travel.
Really? Time travel? Like going to a big, weird machine and traveling to the Stone Age time travel?
My TARDIS is not weird.
My DeLorean is not weird.
What?
Nothing. Don't worry about it.
Never mind.
Okay. So why don't you guys continue?
Right, of course. Now, before the theory of special relativity was ever introduced, it was argued that humans would never be able to reach the stars.
It was thought that your lifespan is too short to cover such great distances, at least for stars in the near surroundings.
Alpha Centauri is the nearest star to the Earth. After the Sun, it is 4 light years away. It is therefore thought that it would take a round trip, even at the speed of light, 8 years. The sum of our galaxy is something 30,000 light years away. Right, Doctor?
Right. 30,000. Measured it myself.
It was reasoned that a person traveling even at the speed of light would have to survive 30,000 years to make such a voyage.
So before the special theory, it was thought that you would have to travel at the speed of light to make it a short distance, but it would take more than a lifetime to do it?
Exactly.
Great, so I get a long story and still know nothing about time travel.
Well, you won't get anywhere if you don't know a little history.
True, saved my life a couple times.
Same. What if you travel back in time and end up in a building or on fire? Look, the amount of energy required to propel, well, anything really to the speed needed for time travel is billions of times the energy to put, say, a rocket into orbit.
Also, counting the radiation induced by these high speeds is a huge issue.
So, even if you could reach the speed, it would tear apart your ship.
Which means time travel is impossible.
Absolutely not.
No.
So what does it mean then?
In this time, the right components and amount of energy is near impossible. Still, time travel is very, very, very possible.
Exactly. If these problems were overcome, time travel would be possible, and you could visit your great-great-great-great-great-great-great-grandchildren for 5 years, and then come back and the present for dinner.
Definitely. Now, was that good enough for you?
Yes, this is actually great. I'm positive this will give me an A from Mr. Cable.
Well, if you think that is good, wait until you hear this. See, Einstein discovered that when you take an immovable object and an unstoppable force and... Oh! Doc!
Doctor!
Ah! Clara, I said to wait in this TARDIS. I said specifically not to wander off.
Well, you can't expect me to wait that thing all day.
Marty, I thought I told you to stay in the DeLorean.
That's just the thing, Doc. Its car's gone. I stood out for a minute to stretch my legs and it just disappeared.
Great Scott! It could be anywhere! Or any wind!
Well, come along then. We'll help you find it. We can use the TARDIS. Come on, we've got a car to find. Well, you're coming, aren't you? When I said everyone, I meant everyone, and that means you.
Really?
Of course. Geronimo.